So for today, we are going to cover the fourth lecture. So which is we are on this part already. So we have done the part on the basic introduction to what is heat and momentum transfer, right? And then for the last 2 weeks, we talk about the molecular momentum transfer. So now if you look at it, right? So I wonder if you notice this keyword here, molecular. So for these few weeks, right, this 4 week, right, what we cover is about transport phenomena, right? So there are two modes of transport, right? So where one is due to the molecular motion and another one which is due to convective transport. So what we are covering now is on this section here for both momentum and also we'll be covering the momentum transfer section and then also the heat transfer section. So for your molecular heat transfer, there will be two sections. All right, so we will need 2 weeks to complete this. One is you'll notice that what we will be discussing today mostly are revisit back what most of the part that you have learned during your heat transfer. We need to revisit back the basic. All right, so that's the basic heat transfer part where we will discuss for today. We'll discuss about the conduction, convection, and radiation. And then for this, we are going to look at also if we have the case in series or in parallel and also in different geometry. So this would be what we are discussing today. All right. And then for next week, we'll discuss on how to formulate the temperature profile using the shell momentum balance method temperature profile. All right, so today one is still quite okay. So just a quick one to recap back what we have learned so far, right, since week one. So week one we discussed about the transport phenomena, transport mechanism, which I mentioned just now. There are two types, the molecular and the convective transport. Then we also look at the different constitutive law, right? So for momentum transfer, we have the Newton law of viscosity. So for today, right, when we talk about heat transfer, then it will be the Fourier's law. When we talk about heat transfer by conduction, we'll deal with Fourier's law. All right, and we also have for mass transfer, if you recall back, we have the Fick's law. All right, so then we also look at some general terms and mathematical operators. So now for molecular momentum transfer, week 2 and week 3, we have discussed about how to differentiate between Newtonian and non-Newtonian fluids. All right, and then we have also looked at dimensional analysis and shear stress and power law of fluid. And then we talk about the flow condition by calculating the pressure drop, all right, and also calculating the general Reynolds number for non-Newtonian fluid. And then we talk about overall momentum balance last week and how to derive the velocity profile using a shell balance method. Okay, so that's what we have done so far. Now, for week one and week 3, right, week 1 until week 3, our focus is more on flow behavior and the formulation of velocity profile. So for this week, okay, our focus will be on the second learning outcome here, which is related to analyze the thermal behavior of engineering system using the laws of conservation. So if you look at your continuous assessment breakdown, right? So this will appear in your assignment too, and also your final exam. So usually for this one, let me recall, it will usually be around your question 2. It may be in your question 2. So as for your assignment, it will be what we are covering next week, right? But I'm planning to post it tomorrow. I'll try to finalize it and then I'll post it tomorrow so that you can have a look first. But for the 2 question, you will only learn about the topic by next week, right? But I'll post it together with also the lecture note for you to have a look first, right, before I teach you all. Okay, so today we'll focus on analyze the thermal behavior using the law of conservation. So this is what we are going to discuss today. We'll revisit back what is conduction, convection, and radiation, and then we'll talk about the Fourier laws for heat conduction, because this would be the basic to what you are going to do next week when you are going to formulate the temperature profile. All right, and then we'll look at one-dimensional conduction. So when we talk about one-dimensional conduction, which means the heat transfer only in one direction. All right, so it could be in X direction, depends on whether it's Y direction or Z direction. Then it will affect how you are going to write the differential equation for the Fourier laws later. Actually, depends on the direction of the heat conduction. So we are going to look at for the case of slab, cylinder, as well as the sphere. Okay. Then after that, we'll talk about conduction through solids, if it's in series and in parallels, and then we'll revisit back also on how are we going to do the calculation for heat transfer if we have the case of convection and conduction. All right, and lastly, we'll talk about overall heat transfer coefficient, the U value. Okay, now, so if you see anyone in the session, they are trying to admit, right? Please help to admit your friend into the class, yeah? All right, because I will be teaching, I will be quite focused. Okay, I may overlook the screen because I'm using another device to teach, so I could not see who is joining the session actually at the moment while I'm teaching. All right, so now let's start. All right, so what is heat transfer? So you have to remember heat transfer and thermal energy are two different things, right? When we talk about heat transfer, it's a form of energy in transition. So for example, the potato, the baked potato, let's say if it's at a higher temperature, so it's just hot out from the oven 120 degrees Celsius, let's say, and your environment is 25 degrees Celsius, you want to cool it. All right, so heat transfer is only recognized when the heat is being transferred across the boundary. Okay, that's heat transfer. You can see heat transfer is the thermal energy in transit due to temperature difference. So there must be a temperature difference between two systems. All right, and so what is being transferred is actually the thermal energy. The thermal energy is possessed by the system, right? But heat cannot be possessed by the system. Heat transfer is not a form of property, but thermal energy is a form of property. Okay, and it's associated with the translation, rotation, vibration, electronic states of the atoms and molecules that comprise the matter. So, so this thermal energy is due to all the activity of the molecules at molecular level, so more to link more to the kinetic energy. All right, so it does not include the internal energy part, right? It's more related to the kinetic energy at the molecular level. So that's why you see it mentioned translation, rotation, vibration, and electronic states. All right. So now let's look at some of the symbols so that we synchronize, right? So that everyone will use the same symbol for this module. Now, when they talk about thermal energy, for some reference, you'll notice that they use the big U, all right? So don't confuse this with the overall convective heat transfer coefficient, right? They use this big U here, the big one, so which means it's in kilojoule, while the one which is usually in small letter, which means it's per unit mass basis. Okay, so so thermal energy is something that is possessed by the system. It's a property. All right, energy associated with microscopic behavior of the matter, while temperature, it's a scale, right? It's a physical quantity where it allows you to denote how hot is the system or how cold is the system, right? It's an a means of indirectly assessing the amount of thermal energy stored in the matter. So as we know that there are different scales. We have the Kelvin scale, the degree Celsius, the Rankine, all right? So and the Fahrenheit scale as well. All right, so but we will be using Kelvin and degree Celsius more often. All right, so then the last one, which is we mentioned just now, the heat transfer. Heat is a form of heat, right, energy in transition due to temperature gradient. Okay. And then, so for this module, the symbols that we are going to use when we talk about heat, which is this one, all right, so this is in kilojoule or joule, you can express it or in joule as well, right? When we talk about heat, we are going to use the capital letter. If it's the rate of heat transfer, for this module, they are using the small q. Last time we used to use the one with over dot, right? So for most of the reference in this module, right, the lecture notes and the tutorial solution, right, when you see the small q, which means it's the rate of heat transfer, right? So which means is energy transfer per unit time, thermal energy transfer per unit time. So if it's heat flux, which means it's equals to the rate of heat transfer divided by area. So you can see that for this module, they use this double prime. All right, so it has a unit of watt per meter squared. For this one is watt. For rate of heat transfer is watt, or is written as sometimes as joule per second. Okay. Now, as we know, there are three modes of heat transfer, right? Conduction, convection, and radiation. So let's quickly look at their definition, right? Formal definition. So as we know, when we talk about conduction, so it requires medium, right? And the medium, it could be a stationary fluid. It has to be stationary, right? Because if it's moving, some fluid that is moving past the surface, then it's convective heat transfer. So if it's conductive heat transfer, then it has to be a stationary fluid, which could be either gas or liquid. Okay, and then it's due to random molecular motion of the atoms or molecules, or if it's electron. So for heat conduction due to the motion of electron, this occurs more often in metals. It's more common in metals, while in gas or liquid it's more is mainly due to the random motion of the atoms and molecule if it's gas and liquid. So for conduction, it requires medium. It could be solid or stationary fluid, which is gas or liquid. So what happens during conduction? So let's say you have two boundary, right? If this is solid slab, right? So one boundary, okay, so it should be at a higher temperature. Well, at this boundary here, so it could be at a lower temperature. So this point here, the level that I put, right, is used to denote how high or how low the temperature. But you should always understand it as throughout the whole surface, right? Throughout this whole surface here is at a homogeneous temperature of, let's say here, T2, right? This is just used to denote the temperature profile, right? While this one is at a higher temperature, T1. So how we draw it, your temperature profile, if it's by conduction, it will be a linear line, right? A linear curve, right? And then it's downward, where heat transfer down the temperature gradient if T1 is smaller, if T1 is higher than T2. All right, okay. And if these two temperatures here remain constant at any time, which means the heat transfer through the medium, right? So the heat transfer through the medium, or the rate of heat transfer, will always be constant as well. Same goes to the flux if we are dealing with a slab, right? If we are doing the slab, your heat transfer, the rate of heat transfer and the heat flux would be constant with time, right, at steady state. So this applies to slab only. But if it's cylinder, then it will be different, right? Your rate of heat transfer will be constant, but the heat flux, it would be different, right? For cylinder and a sphere, because heat is transferring through varying cross-sectional area. Okay, so we'll come back to this again later. All right, so then the next one, when we talk about convection, that's the heat transfer that occurs between a flowing, a flowing fluid, right? A flowing fluid past a surface. So how to phrase it is heat transfer due to combined influence of bulk and random motion of fluid flow over a surface. Now, so what actually happens during heat transfer by convection? Let's say this is the plate, and then you have a fluid flowing. So last week you learned about the velocity profile, right? And then when we talk about it, so this here, so actually what happens is you have a thermal and a velocity boundary layer. So sometimes they may intersect with each other. So something like this. Let's say this is the thermal boundary layer. This is the velocity boundary layer. So you know that what happens is, right, your velocity boundary layer will looks like this, right? The velocity profile, right? Actually, what happens to temperature profile? It's also somewhat like this as well when we have convection. All right, so where you know that usually at the layer which is very close to surface, right? So that's the viscous sublayer. Most of the fluid, it travels in a streamlined manner. But when it's further away, right, then you have eddies. All right, so that's why you can see here at the region very close to the plate, right? Your the temperature variation is actually higher because most of the heat transfer here, because fluid is flowing in streamlined manner, so which means most of the fluid here, heat will be transferred mostly by conduction. Only when it's further away, right, from the surface, there will be a lot of eddies, right, that bring about a motion of the fluid, right, the parcel of fluid moving from here and there, which your convection will mainly occurs. And then it's that section that the temperature profile, it will looks more uniform, right? The curve is the gradient is lesser. Okay, so later we'll in towards later weeks, right, we will talk about the thermal boundary layer and the velocity boundary layer, and then it can be related by the Prandtl number. So we'll talk about it later. Right. So what happens in convection is actually a combine of the conduction and convection at the same time, actually. All right. So similarly, all right. So you need a temperature difference, right? The surface is at let's say Ts, which is higher than the ambient temperature. Then the heat will transfer from the surface to the moving fluid. So same thing for convection, you need a medium. So for this, it will be the flowing fluid, which is either gas or liquid. All right. So then for radiation. So radiation does not, it doesn't need a medium. So as long as if it's a surface, right? So let's say if you have these two surface here and then sandwich between them is certain gas. So as long as the surface is at a higher temperature than absolute zero, right? 0 Kelvin. As long as the surface it has a temperature above 0 Kelvin. So then heat will be emitted in the form of radiation, electromagnetic wave to the surrounding. Right? So energy that is emitted by matter due to the changes in the electron configuration of its atoms and molecules, and is transported as electromagnetic wave. All right. So example of radiation, it could be then be the sun, right? Heat transfer from the sun. Okay, or sometimes even you can feel if any hot surface when you bring your hand near to it, right? You will feel the heat that is released in the form of by radiation. All right. So here for radiation, that is transport that does not require a medium, and it's occur most efficiently in a vacuum. So we have briefly talked about the modes of heat transfer. Oh yeah, and one thing, right? So when we talk about convection, don't forget we have two types, right? One is by natural convection, okay, natural convection, and then we have also forced convection, right? So where natural convection is due to density difference, right? Density difference, where this one you need a forced motion to cause the fluid to flow. Usually maybe it's by a fan, right, or something else. Well, for natural convection is due to density difference. For example, if you are heating a liquid, right, so we know that at um, at high temperature, the density, let me recall back, density of the liquid, let's say we take for example water, right? At high temperature, density of water will decrease. So when this layer of fluid is being heated, then it will travels up. But the water which is at the upper region here is at a lower temperature, the density is higher, so it will then sink to the bottom. So in this way, when the heating is continuous, which means you have more fluid, right? More water is being heated and density will decrease, so it will travels up, while those cooler one, it will sink to the bottom. So in this way, it will then create motion of the fluid. So you notice this very often when you are doing shopping, right? When you are any shopping mall, you notice that when you go higher floor, especially mid valley, right? The higher the floor, right, it's very warm, but when you go to the lower floor, it's very cool. That's because of the gas, right? Similarly, air when it's at higher temperature, it will the density decrease, so it will flow up. Well, when the air is cooler, it will sink to the bottom because of higher density. Okay, okay. So that's convection. All right. So if you have time, if you want to know more how the heat transfer occurs and then the discussion at molecular level, you can refer to this link here, the video by Professor Dave. It's only around 4.42 minutes. All right. So if you're interested, you can explore it. Okay. So now, I believe should be fine, right? It's the revisit back of some basic concept of the three different modes of heat transfer. So now we are going to look at the Fourier law so that you have a very good understanding on the equation part, because next week onwards then you need to derive the temperature profile. All right, so Fourier laws for heat conduction. Okay, so as we know, right, so for conduction is the transfer of thermal energy, right? So and that is due to molecular motion. So it will be motion of the atoms of molecule for gas or liquid, and then if it's for a case of metal, then it's more due to the motion of the electrons, and then it usually occurs down the temperature gradient, so such that it's the heat, right, energy from more energetic particle, right? So the more energetic particle that being transferred to the less energetic particle. All right, and then yeah, okay, this I have mentioned it. So let's look at here. So it's a combination. So you can see here, depending on the nature of the substance, whether it is gas, liquid, or solid, the particle motion consists of one or a combination of random translation, internal rotation, and vibration. And therefore, sometimes they also call it as a conduction as a diffusional process, right? Which is similar to what happens in mass transfer, where it's due to concentration gradient. All right. So in summary, right, which means during conduction, what happens is the thermal energy is diffused from higher temperature region to lower temperature region through the molecular collision as a consequences of all those translational, the rotation and the vibration of the molecules or the electrons. All right. So okay, and then when we talk about the temperature, which means if you know that the temperature, let's say at one boundary is very high while another is lower, so which means the boundary or the region where the temperature is higher, it will possess more thermal energy. Right. So now let's look at this diagram here. So let's say, all right, you have a solid, all right, and then at two different boundaries. So let's say if it's a solid, all right, so something like this, all right, and solid, all right, and then at the start of the, let's say, an experiment, okay, so this solid here, it has a thickness of y, all right, and at times smaller than 0, each of this boundary here, each of this surface here is hold constant at temperature T naught, initial temperature of T naught. Now, then at time equals to 0, so let's say the bottom plate here is suddenly heated, all right, or suddenly bring to a temperature of T1, while this boundary here or this surface here is still remain at temperature T0, right? So the lower plate is suddenly raised to a temperature of T1. So you notice here the when how they draw the temperature profile is that here temperature T1, okay, temperature T1, but at time T equals to 0, within the solid itself is still constant at a temperature of T0, right? Then at a very small time T, right? So let's say at a very small time T, because there's temperature difference between two surfaces, right? One at the lower boundary, right? The lower surface is at T1, upper surface is at T0. So you can expect that there will be random molecular motion, right? In this region here, right? Where the more energetic particle, it will then start to rotate, translate, and vibrate. And then with this, the thermal energy is then transferred to the next neighboring particles, which is with lesser energy. So at this time, if we look at it, your temperature is a function of both y and t. Okay, so what does it mean? So you have to recall back, all right? So we always has to assign the direction, the coordinates, right? So this is the x direction, this is the y direction, right? The vertical up is the y direction. So what happens is you have a lower and upper plate with the lower plate at higher temperature, which means the heat will transfer from higher temperature, the lower plate, to the upper plate, which is at lower temperature. And with that, what happens is the heat is transferred in the y direction, right? The heat is transferred in the y direction from lower plate to upper plate. So, and at very small time t, your temperature profile is not developed yet. So you can notice that the temperature now, it varies with the position, right? It's position from the lower plate, and at the same time, it also varies with the time. All right, at very small time t. So because right at very small time t, the more energetic particle, it transfers some energy to the lower energy particle, right? But it's only maybe the energy transfer hasn't penetrated deep enough into the solid yet. So that's why you can see here, right? So when they draw the temperature profile, yes, and the lower plate is at T1, right? But you can see the temperature variation is still not penetrate deeply enough into the plate, into the solid. All right, so then the rest of the solid is still remain here at temperature T0. But when the time is sufficiently large, right, is sufficiently long already, so then the temperature and the thermal energy transfer is more deeply into the solid. So now we can see that the temperature profile is in this one here is T1, all right, and then it's a linear curve where at another boundary here is at T0, still maintained at T0. And during this time, when time is sufficiently large, your temperature is a function of y only, the distance from the lower plate, right? And it's function of y because your steady state heat transfer has been achieved when time is sufficiently large, right? So you have achieved a steady state heat transfer, and then a temperature distribution profile is for steady state is already established, all right? So now, if we want to maintain these two surface here at temperature T1, okay, at temperature, so if we want to maintain these two surfaces here at temperature T1 and T0, which means you have to maintain a constant rate of heat transfer, right? There need to be a constant rate of heat transfer so that these two temperature here will remain constant. So now, if you look at here, the Fourier law equation, right? So it's where the rate, this is the rate of heat transfer, right? The rate of heat transfer divided by the cross-sectional area. So the cross-sectional area, as we know, then it would be this one, right? It's always the area that is perpendicular, right? So the area that is perpendicular to the direction of the flow, right? So the y direction. So this would be the area, okay? Then this would be the thermal conductivity, right? So you need to recall back all this term already. The thermal conductivity is equal to thermal conductivity multiplied to the temperature difference. So you can see it's T1 minus T0 divided by the thickness, right? The thickness of the plate or the solid. Or you can look at it as the distance of the diffusion, the heat transfer part, molecular heat transfer part. Okay, so then how are you going to express it in terms of the constitutive law, the Fourier laws in differential equation form? Because that's what you'll be doing next week. So now, as we know, the rate of heat transfer divided by area, you can denote it as the Q with double prime. Now, you can see it's written as dt dy, the rate of change of temperature in the y direction, because it's written as dt dy here. If you recall back last time, whenever you learn is negative k dt dx, right? Because that's the case where the heat transfer, okay, let me draw this, because this one here, the heat is transferred through a solid slab in x direction. But what we are discussing just now is heat transfer in this one, in y direction, okay? So that's why your temperature also varies in y direction, right? When it's closer at y equals to 0, so this is 0, okay? So this is y equals to 0, and then here is y equals to the big Y. All right, so at y equals to 0, the temperature at this surface is at T1. Well, at y equals to the big Y, sufficiently far from the lower plate, temperature is T naught. So your temperature actually varies in the y direction. So that's why it's written as dt dy. So then if it's for this case here, then your heat flux equation, it will be written as negative K, the temperature variation in the x direction, right? Because here at x equals to 0, T is equals to T1. At x equals to L, let's say the thickness is L, at the T temperature is equals to T2. So temperature varies in the x direction. So it depends. If you have temperature vary in the z direction, then it will be written in this form. All right. So, or if it's the case where you have temperature vary in all three directions, then you can see that it can be expressed as the negative K, this one del operator of temperature. Right? If we have temperature vary in all three directions, so then it's written in this way here is the negative of the sum of the partial derivative of actually the temperature, right? This is if it's just the del operator. If it's del T, then it's the sum of the partial derivative of the temperature with respect to x, y, and z direction. All right, and you can see here we have the negative sign, right? Same like what happens to the Fick's law as well, right? So because this one, the heat is transferred down the temperature gradient. Okay, now, so next, we will then look at how to, later we'll look at how to solve this equation here. But before I proceed to the next, any questions so far about this slide? Any question? No? Okay. Oh, okay. Thanks for confirmation. Yeah. All right. Then I'll proceed. Now, so, okay, that's the foreign law. So take note that when we are talking about the rate of heat transfer, then it would be in watt or joule per second. If it's heat flux, so in this case here, all right, this is the heat flux. Heat flux, then it will be watt per meter squared. All right, so if you're going to calculate area, so which means you just rearrange it, then you'll get back the negative Ka dt dy. All right, so now, and which means then if you look at it, your thermal conductivity, it has the unit of watt per meter Kelvin. Okay, watt per meter Kelvin. All right, so now let's look at the equation, how we are going to use it. Okay, so by now you should know that conduction, right? So it's governed by Fourier law. So let's say if we are analyzing one-dimensional heat transfer across a slab, right, as shown in this figure here, where the rate at which the energy or heat is conducted, right? So the Q, the rate of heat transfer across this thin strip here, across this thin strip with a thickness of delta x. So it's the rate of heat transfer is proportional to the temperature difference, and it's also proportional to the area, but inversely proportional to the thickness. Okay, the thickness of the slab. So which means if the area is even larger, then you should have more effective heat transfer, and the higher the temperature, the larger the temperature difference, the higher the rate of heat transfer. All right, so when we work with the equation, okay, just a quick one, I'll go through with you. So in this case here is if you assign the coordinates, now we are discussing of for heat transfer in the x direction, right? So let's say at this region here, this we denote it as x1, all right, and then this boundary here, right, this second surface here, right, is at position x2, okay, and this one here, let's say at x1, the temperature is at T1, and then at x2, temperature is T2. So you have to assign the boundary, all right, and we are dealing with heat transfer in the x direction. So according to your Fourier laws, right, then it will be expressed as the rate of heat transfer divided by area, negative K, the rate of change of temperature with respect to x direction. All right. So we'll do a quick one to solve this one here. So rearranging. So we know that the rate of heat transfer, right, if it's at steady state, this would be a constant value, right? Suppose if it's at steady state. If you're dealing with steady state heat transfer, it's a constant value. And in this case here, we are dealing with slab. The area is constant as well, right? For the case of slab, right? Because it's slab. Okay. So if this is a constant value, so the next thing is we will need to rearrange the variable. So we'll integrate this constant value here with respect to x. And then on the right hand side, the thermal conductivity, it depends. All right, so you may need to make an assumption, right? So usually if you recall back, what assumption we'll make is we'll assume, right, the K is thermal conductivity is constant over the range of temperature investigated, because thermal conductivity actually will affect by the temperature, but we can make some safe assumption, right, to assume that it's constant over the range of temperature investigated. Then this will be constant. Then we'll integrate this with respect to temperature. All right, then next thing, before you can proceed, you need to assign the boundary. So which is mentioned just now, at boundary x1, right, the temperature is T1, and then at another boundary x2, the temperature is T2. Okay, so then completing this integration here, okay, so you should have, you're integrating as if this is 1, right? Here is also 1. Okay, so you integrate 1 with respect to x, you get x, so it will be, the boundary will be x squared, x2 and x1, right, that equals to negative k, right? Integrate with respect to temperature, so T2, T1, right? Then you expand it to x over a, so it's x2 minus x1, negative equals to negative k, T2 minus T1. All right, then you can rearrange it. The rate of heat transfer in the x direction divided by area, it will be, so you can then start to treat this one, this negative here, don't forget it. Sometimes the student really forget this one. All right, so rearranging it, so you get T1 minus T2 divided by x2 minus x1. Okay, so this is the equation that we usually use to calculate heat conduction through slab. All right, heat conduction through slab. Okay, so should be fine, right, for this one. All right, so it's okay if you have time, you can practice this, because later when we do the formulation part, you need to do this as well. All right, okay, now, so, okay, so let's say if you have this equation, okay, if you're interested on how the temperature will vary with the distance, right, with the distance, then you can substitute some value here, right, some value here to find out. Let's say if you know what is the rate of heat transfer, right? So if you know what is the rate of heat transfer, and you would like to know how the temperature varied within the solid itself, then you substitute the rate of heat transfer, and then you substitute what is the distance, right? Then you should be able to find out, let's say, the temperature which is at some distance here, let's say x3, right, to find out what's the temperature at some point T3, which is, if you look at here also, right, so you notice that it's a linear equation, right? There's no square within the equation as well. So that's why your temperature profile, for example, at x1 is at a higher temperature T1. All right, so if you substitute some x value here into this equation, then you should be, then you should be able to find what is the T2 somewhere here. Right, so then at x2, the temperature is dropped to T2. All right, so this is the temperature example of a temperature distribution profile if you would like to plot it on a graph. Okay, so is there any questions so far for this one? Any questions so far? Okay, I think no also in the thanks Junhan. Thanks Junhan for confirmation. Yeah. All right. So then, okay. All right. So as mentioned just now, right, we mentioned that, so what we did just now is we assume that this is a constant value. Then this would be the equation that we are using, right? So if you are calculating heat rate, then you just need to rearrange this equation. The heat flux is equals to the rate of heat transfer multiplied, oh sorry, hold on. Okay, this is error. So heat flux is watt per meter square, right? This is equals to heat flux, qx, right, divided by area is equals to heat flux. So which means if you want to find the rate of heat transfer, then it will be the flux, right? Heat flux multiplied to the cross-sectional area. Now, talking about this, so the thermal conductivity, most of the time that you have been learning so far, we assume that it's constant. So let's say if the thermal conductivity is not a constant value, so but it will vary linearly with temperature. So the treatment that they are going to do is by using this equation here. All right, so we'll take then the mean value of the thermal conductivity, which is some coefficient A, right, some empirical constant A and B, right, A plus B multiplied to T1 plus T2 divided by 2. All right, so this will then give us the mean value of the thermal conductivity for because your two surfaces at different temperature, right, at T1 and T2. So they will give you, by using this equation, you'll give us the average value of the K between these two temperatures. All right, so then if you substitute it back to this equation, then it will looks like this, right, where this is the mean value of the thermal conductivity, right, where A and B are some empirical constant. But no worries, for this module, most of the time when we do calculation, we are still assuming that the K value is constant. All right, so the K value is constant. So this is an introduction for your knowledge. All right. Okay, so that's the end of the part on the Fourier laws equation. So the introduction part. So now we are going to look at what if we need to apply it to the case of slab, hollow cylinder, and sphere, especially these two. Okay. Okay, so now when we talk about heat conduction, so when you see that it's divided by x, right, which means you can expect that the heat transfer is in the x direction, right? The heat transfer is in x direction. So if you recall back, the heat transfer, the general equation, so let's talk about the general equation, is the temperature difference, which this is the drying force, right? This is drying force for heat transfer to occur. It's temperature difference divided by the sum of resistance, right? This is the sum of resistance. Okay, this is the most general heat transfer equation. Okay, so then if it's the case for heat transfer by conduction, which means this part is the drying force, then you need to rearrange this, right? So rearranging it, you get delta X divided by Ka. So this section here, it will then be the resistance to heat transfer, which makes sense, right? The thicker the slab, right, then the slower the rate of heat transfer, you have higher resistance to heat transfer. Also, actually, the area, the larger the area, right, the more effective the heat transfer, or the higher the K value, as we know, right, the more, the better the heat transfer will happens. All right. Okay. Now let us look at the Fourier law equation for the case of cylinder. So now what we have been discussing just now is for Cartesian coordinate. If it's cylindrical coordinate, what happens is, so let's say if you have this cylinder here, the inner wall, okay, let's say, let me see, what's the notation they use? Okay, still T1, T2. Okay, so let's say the inner wall, right? So this cylinder here, it has a inner wall, all right, so with a radius of R1. This is R1. And then the temperature here, let's say we denote it as T1. Then we have the outer surface of the cylinder, right? Let's say it has a radius of now R2, right? And then along the whole outer surface, it has a uniform temperature of T2, right? So if let's say T1 is greater than T2, right, so which means the heat will then transfer through the wall of the cylinder here by conduction, right? So we're talking about the wall of the cylinder only. So heat transfer will be by conduction radially, right? It's in radial direction. Okay, so if it's in radial direction, so you'll notice that just now the Fourier law now is expressed in terms of dr. Okay, and for this area, it's also the area which is normal to the direction of heat flow is this one here, is cylindrical, the cylindrical body, right? The cylindrical body. Okay, let me highlight it. this part, the cylindrical body, and then it's actually the area is actually increasing in radius, right? Because heat transfer by radially. So, and then for this cross-sectional area is expressed as 2 pi RL. So substituting it, so it will be Q, the rate of heat transfer, divided by 2 pi RL equals to negative K dt dr. All right, so now just a quick one. I'll redo it here so that you can, you have a focus at least, okay? when I describe it, rather you see a screen without any action going on. All right, so okay, so if you look at this equation here, before we solve it, the radius is a variable, right? The radius is variable, whereas the rate of heat transfer, the length of the pipe, the thermal conductivity are constant value. So we will rearrange the variable. So Q divided by 2 pi L is constant. We'll be integrating 1 over R respect to the radius, right? And then here on the right-hand side, we'll be integrating it respect to temperature. So we assign the boundary, right? Just now we mentioned at R1, temperature is T1, at R2, temperature is T2. So solving this, okay, so integration of 1 over R divided by 1 over R with respect to R, if you recall back, is R to the power, okay? So in this case, it's negative 1, right? So negative 1, oh, okay, this is different, okay, sorry. Integrating with respect to 1 over R, you get ln R plus C, right? Okay, this one, ln R plus C, okay? So, which means, okay, now 2 pi L, all right? So, it's ln R, R1 to R2, okay? Then negative K, okay, integrating it, you get temperature. Boundary is T2 and T1. So if you expand it, let's do it step by step, in case some students still confused. Then it will be ln R2 minus ln R1 equals to negative K, right? And then here you have T2 minus T1. Okay, so and for this one here, if you recall back, right, so according to the maths rule, right, so Q over 2 pi L, so ln R2 minus ln R1, it can be expressed as ln R2 divided by ln R1. All right, here rearranging it, we can express it as T1, K multiplied to T1 minus T2, and then further rearrange it further. Okay, so you have K multiplied or 2 pi LK, all right, and then multiplied to T1 minus T2 divided by ln R2 over R1. Okay, so this is the equation that we usually use to calculate the rate of heat transfer through a cylindrical wall, right, by conduction. Okay, so if you want to, if you rearrange it, which means in the form of drying force divided by resistance, right? So it's T1 minus T2 divided by 1 over 2 pi KL, right? Then ln R2 over R1. This will then be the resistance term. Okay, all right. Well, the top part then is the drying force. No. So for this module, right, when you're at this level, yep, this is what you learned last time, right? So, or it depends if the area. So let's say the outer surface area, right, of the pipe, right, divided by the inner surface area of the pipe, A2 minus A2 divided by A1. If it's smaller than 1.5, then we can calculate the area as the average, right? So A1 plus A2 divided by 2. But if it's the case where A2 divided by A1 is greater than or equals to 1.5, right? The equation can be expressed in this one. Instead of what we do here, right? This one here, all right? So we can also use this for calculation. So if you look at it, it's as if very similar to a case where we have the rate of heat transfer by conduction, right? Where you have Ka multiplied to T1 minus T2 divided by X2 minus X1, if you compare it. Okay, so if it's the case of A2 divided by A1 greater or equal, so which means greater or equal to 1.5, all right, so the equation can be expressed as K multiplied to the log mean area divided multiplied to the temperature difference, then divided by the outer radius minus the inner radius. Okay, so for this module, right, so if it's the case when we deal with cylinder, we are going to practice using this formula here, where this log mean area, the concept is the same as the log mean temperature. So you can see that it's the outer surface area of the cylindrical body minus the inner surface area of the cylindrical body divided by ln A2 over A1, which you know that for the cylindrical body, right, the area is A2 is equals to 2 pi R2L, right? Okay, and then for A1 is 2 pi R1L. Okay, all right, so then you substitute here. Right, so for tomorrow, the tutorial, right, so we'll practice this for the case when we deal with cylindrical body. Okay, then the next part, we are going to talk about the hollow sphere. So for hollow sphere, so we start from here, right, because hollow sphere is the same thing where your rate of heat transfer is through a spherical body where the cross-sectional area of the sphere also is varying in the radial direction, right? The cross-sectional area is varying in the radial direction. And then for this area, for sphere, it's expressed as 4 pi r squared. All right, so then when you solve it, okay, let me just go through it quickly with you. All right, so Q over 4 pi r squared equals to negative K dt dr. All right, so if you notice, right, we are writing it as the one that is not in italic because your temperature only varies in radial direction. If your temperature varies in more than one direction, then it will be expressed as a partial differential equation, which you learn how to do it later, right? When you are introduced to, we call it the equation of change of temperature. Okay, now let's solve this. Okay, this r squared here is a variable. All right, so then we'll factor out the Q over 4 pi. We'll integrate 1 over r squared with respect to the r. Then we'll integrate the thermal conductivity with respect to temperature. So let's say, right, at the inner radius of the sphere, R1 here, right, the temperature is T1, right, so let's say T1, and then at R2, okay, at R2, so it's mentioned here is T2. R2 is T2. So now, if we are integrating 1 over r squared with respect to r, right, so it's equals to negative r to the power of negative 2 plus 1 divided by negative 2 plus 1. So that's why you get, right, negative 1 over r, right? Negative 1 over r. Oh, of course, plus c, okay? Plus c, okay? So then, okay, coming back here, let's complete the integration. Okay, so you have negative 1 over r, and then you can denote the boundary. And then on the right hand side is negative k, temperature, T2, T1. All right, so then continue here. All right, Q over 4 pi. So you have negative 1 over R2 minus negative 1 over R1. Okay, and that equals to negative K, T2 minus T1. So if you rearrange it, so your Q, rate of heat transfer through a spherical body, all right, a hollow spherical body in radial direction, so the rate of heat transfer will be equals to, so 4 pi k, all right, negative, I'm going to rearrange it, so you'll get T1 minus T2, and then divided, so we will rearrange this as well, so it will become, so negative, negative, it will be positive, so 1 over R1 minus 1 over R2. So that's how you get this equation here, for rate of heat transfer through a hollow spherical body. All right, and yeah, through a hollow spherical body. Okay, so any questions so far on solving the integration part to get the equation? Any questions so far? Okay, let me see what is the next slide. Because it's 11 already. Okay, the next part we are going to talk about conduction through solid in series. We'll release it back. All right, so it's 11 now. I think let's take a 5 minutes break. Right, let's take a 5 minutes break. Then I'll show you the camp scope. Then 11:05 we'll come back and continue on the last three part. Okay, let's take a 5 minutes break. Okay, it's 11:05. All right, so okay, I'll copy and post the passcode in the chat area. I think there are another 3 students yet to take the attendance. Right, so you still have 5 more minutes for the passcode. Right, so I'll continue with the lecture. Okay, let me share the lecture notes. Okay, now let's continue. So we just now we have covered the part on how to derive, right, and solve the rate equation for the case of slab, hollow cylinder, and hollow sphere. So what if we have conduction through solids and in series and parallel? So a quick one. So this happens if you recall back, it could be a case of let's say if you have any packaging materials, right, they're made of different materials that is being layered in series, or it could be the wall of some equipment like your oven or your fridge, right? Well, each side of the wall it has several layers of different types of materials. So the heat conduction then, it would be the case where you have heat conduction through composite plane walls in series. So if the temperature at each surface remain constant, if you recall back at T1, right, let's say at this surface here, and then at the outer surface is at T4, if the temperature remain constant through time, then the rate of heat transfer through each layer, so Q, right, denoted by Q, it will then be constant. Okay, so if we express the rate of heat transfer for each layer, all right, so let's say material A, it has a thickness of delta XA, material B, it has a thickness of delta XB, and then here, material C, delta XC. So expressing the rate equation, you can see here, right? So in general, it will be the thermal conductivity multiplied to the cross-sectional area, then divided by the thickness, right? Divided by the thickness of each material, then multiplied to their drawing force of across each slab, right? The temperature difference. So now, if we rearrange it, so you rearrange it as T1 minus T2, T2 minus T3, and T3 minus T4. So similarly, the equation has the form of the rate of heat transfer multiplied to the thickness divided by the product of the thermal conductivity and area. Then, if we sum up the temperature difference, all right, so if we can see here, we sum up T1 minus T2, this one, plus, okay, T2 minus T3, and plus T3 minus T4. Okay, and we also sum up the right hand side of each equation here. We'll sum it up. All right, and this is what we will obtain. All right, and then knowing that, all right, so if T1 minus T4, all right, if T1 minus T4 is constant at any time, then so does the rate of heat transfer through each slab, right, which is in series. So with that, then you can factor out the Q value, right? So then the equation, it will then looks like XA divided by KA multiplied to the area, right? Then XB divided by the thermal conductivity of that material B multiplied to area, plus XC divided by the thermal conductivity of material C multiplied to area. Actually, if you want to, you can also, in this case here, you can also factor out the area, because let's say if you're assuming that it's a series of slabs, right? And then it has a constant cross-sectional area. So the area here, it can be factored out as well if we are going to calculate the flux. All right, so here it will then be on the left-hand side, right, negative T2 plus T2, right, negative T3 plus T3, so which means it is then simplified to T1 minus T4, which on rearrangement, all right, so the rate of heat transfer through this composite wall here in series, right, is the drying force, overall drying force T1 minus T4, right, just now, T1 and T4 here. T1 minus T4, then divided by the sum of resistance of each layer, if you look at it, right? So it's as if it's a sum of resistance of individual resistance for each layer. If you look at it, if you are going to draw like an electrical network, all right, So the resistance to heat transfer for this one is XA over KA multiplied to A, and then this is XB over KB multiplied to A, and this is XC, right, KC multiplied to A. All right, okay. So this is the case if we have plain walls in series, whether it's some packaging material or some or the walls, right, they're made of different layers of brick, concrete, right, or then you may have some insulation layer, let's say, right, in Japan, or the equipment, all right, or some equipment or electrical equipment that you are using. So, or you can also simplify it in this form here, right, writing it as the resistance of material A, B, and C. Okay. Now, if it's the case, if we have heat conduction through cylindrical walls in series, right? So you have one layer, all right, second layer, oops, second layer, right, and then another, the third layer. So if you have three layers, so what happens is the heat is transferred through the cylindrical walls, all right, in series, and then it's radially. Okay, so if you recall back, this is the formula the new formula that we learned this semester, right? So rearranging it, you have the temperature difference, okay, then you have okay, R1 R2 minus R1 divided by K multiplied to the log mean area. Okay, so now for each, you can see, right, for the first layer for material A, right, so it's the thermal conductivity multiplied to the log mean area of material A, which means if you express it as ln A2 minus A1, okay, it's not ln first, it's A2 minus A1 divided by ln A2 divided by A1, right, so which means you need to calculate what is this area here and this area here. Okay, then when it comes to the second material, all right, let's say you have an insulation layer, all right, so let's say if this is a pipe, right, so the first layer is the pipe, the steel, let's say this is pipe, this is the insulation layer, and then this is some cover, right, so some lining, let's say some lining to protect the insulation layer. So this log AB, right, then it will be A3 minus A2 divided by ln A3 over A2. And then this would be A4, right? The outer surface area of the lining, right, or the cladding, minus A3 divided by ln A4 over A3. Okay, so same thing if you rearrange it, right, for each of them, right, using the same method as what we see just now, right? So re-expressing it in terms of we re-express the temperature difference in terms of the rate of heat transfer and then the resistance, right? Then summing up all the temperature, all right? And then on the right-hand side as well, rearranging it, then we will obtain this equation here, which is the same as what you can see just now. It's the overall temperature difference, T1 minus T4, then divided by the sum of the individual resistance, right? So this is for the pipe, for example, let's say this is the resistance for heat conduction radially through the pipe wall. This is the one that is through the insulation layer, right? This is the one, let's say, through the cover, right? Cover lining or the cladding. Okay, that's the final equation. So we'll try one example during the tutorial session for by using this new equation here that you need to practice. Okay, before I proceed to the next part, any question, anyone? For heat transfer in series, is there any question? Okay, all good. Huh? So take note that for this, when you have heat transfer through a cylindrical layer, your rate of heat transfer, yes, is constant. But you need to take note that the flux is not constant because the area is varying in the radial direction. All right, so that's the difference. So when we talk about materials in parallel, so this is a bit more complicated. Let's say if you have one material A here, all right, and then another material B, and on each of its surface at different boundary, at different side is so different, and each material, it has its own conductivity, then the rate of heat transfer in the x direction, you can see that is equals to the rate of heat transfer through material A, right? For heat transfer through material A, and plus the rate of heat transfer through material B. It's the sum of both. All right, so then you just expand the equation, right? What is the Fourier law equation for heat transfer through the material A and material B? All right, so yeah. So yeah, that's it for the material. So example is like if you have heat conduction. So sometimes if let's say you want to thaw meat, the faster way is you put some metal plate, right? Or if you have a metal slab and then you place the meat on it, right? That would be the case where you have heat transfer in parallel then, right? Heat transfer in parallel. Okay. So then we're going to look at the last two parts. What if we have combined convection and conduction? How are we going to count the equation, and how you are going to express each of its resistance term? Now, so now this is an example, right? Which is quite common. Let's say if it's the wall, right, which is made of three different material: the concrete, the cork, and the pine layer. And then at the, let's say at the outer, so let's say during a warm day, right, the outer temperature is T1, while at the inner surface there is exposed to the room air inside the cold room, or if you have an aircon, all right, so it would be at a lower temperature T4. So then definitely, so what happens is then your heat transfer, all right, there will be 5 resistant term, right? One, which is you have heat transfer by convection. So let's say it's natural convection, right? Let's say if it's just wind that is blowing, all right? Wind is actually not forced convection because it's due to density difference and the pressure difference, right? That cause the wind air to set in motion, all right? So then here you have 3 resistance where heat is transferred by conduction through the concrete, cork, and the pine layer. And the last one is heat transfer from the surface of this pine here to the environment. So if we are going to draw the temperature profile, let's say if I'm going to draw it, this 3 layer, okay, it depends on the K, right? But for convection, the temperature profile looks like this, right? It looks like this. Then conduction, okay, and then yeah, it's linear curve. Sorry, yeah. Okay, just 3 layers. Okay, 3 layers. Okay, there's temperature drop. All right, so here then you have temperature drop. So for convection, you can notice that the temperature drop usually is drawn in this manner here, but it's because also the velocity boundary layer, right? So the velocity boundary layer and the temperature boundary layer, which at the section which is closer to the plate, right, heat mostly is being conducted by a bit like by conduction. That's where you have the variation in the temperature most. That's this section here. That's why you see that it's a drop. Then further from there, it's a flat line because that's where most of the heat will then conduct by convection due to there's a lot of eddies, right? There's a lot of eddies. Okay, now coming back to here, all right. So as you know, this one it would then be expressed in this form, right? For its resistance. Okay, so as xc over kc multiplied to A, the area would be the same, right? Because it's a solid slab. While for convection, if you recall back, the rate of heat transfer is expressed as the convective heat transfer coefficient multiplied to area multiplied to temperature difference. So if you rearrange it to this form here, the temperature difference divided by resistance, which means it's temperature difference divided by 1 over HA. Alright, so then for this one, we can express it as 1 over HO multiplied to A. So let's say for outside room, the convective heat transfer coefficient is denoted by HO. For inside cold room, is denoted by HI. So this one, it will then be expressed as 1 over HI multiplied to A. Right, so okay, it's drawn here. So this is an example. all right, a slab. So your temperature profile for convection is drawn in this way here. It's slightly curved. Okay, so then you can see rearranging the equation. Oh, okay, yeah, it's in this one. Okay, let me show you this one. So which means for this one then, your rate of heat transfer, it will be T1 minus T4 divided by 1 over HIA plus XAKA. So the sum of the individual resistance through each layer then. Right, so XCKC multiplied to A plus 1 over HOA. Right, so if you have multiple layers in series where conduction occurs and then convection occurs at each surface, all right, each side of the surface, then it looks like this. Okay, all right, so this is if it's just convection, all right, conduction and then convection. So we can see if you draw the thermal resistance network, there are three resistant terms. Okay, there would be three resistant terms. Okay, one by convection, one is resistant to heat transfer by conduction, and one for resistant to heat transfer by convection. Okay, now, all right. So, any questions so far? Any questions so far for this one? Before we look at the last part. Okay, thanks, Junhan. Thanks, Shavesh. All right. So, okay, let's look at the last part here. So we are going to talk about the overall heat transfer coefficient. So sometimes what happens is, like this question here, we may not know what is the temperature of T2, T3, right? Or sometimes some of the thermal conductivity value is not known. So what happens is we can also excuse me. So if we know what is the overall heat transfer coefficient, we can also use this equation to calculate it, where the rate of heat transfer, right, in watt, okay, is equals to the overall heat transfer coefficient multiplied to area multiplied to the overall temperature difference. Okay, so if you compare, right, so it's the temperature difference divided by the resistance, and then it's also equals to UA multiplied to the temperature. So which means 1 over R is also equals to 1 over UA, right? Or you, hold on, hold on, yeah. Okay, UA. Okay, so rearranging it, so you notice that the overall heat transfer coefficient is also equals to 1 over the resistance multiplied to the area. So that's why when you look at this equation here, you'll notice that all the area term is no longer there, right? If you compare, right? So because suppose this is 1 over HIA, this is X over KA, this is 1 over HOA. Okay, so where this is the sum of the resistance, right? So if you total it up, this is the sum of resistance. But if you multiply both sides with area, so let's say I multiply both sides. So I multiply both sides with area, then this will cancel out each of them, right? And then this resistance multiplied to area is equals to the 1 over resistance is equals to 1 over U. Okay, I should write it in this way here. Okay, 1 over U, it's just rearrangement, right? 1 over U is also equals to RA. Okay, all right. So that's why you didn't see any area term here. Okay, so that's the overall heat transfer coefficient. Now, the overall heat transfer coefficient, it can actually be expressed, let's say for the case of cylindrical wall, it depends. It can be expressed in terms of the inner surface area or the outer surface area. So this is the case, right? Let's say if you have combined convection, so you can see convection and then conduction and then convection, combined convection and conduction through a cylindrical wall. So in this case here, the T1 is at a higher temperature than T4. So this might be the case, let's say in a gas-fired shell and tube heat exchanger, where the gas, right, or the gas or the heat, the hot air, right, that is being, or combustion from the furnace, the hot air travel, and then it will heat up the water that flow past it. So this might be the case. Then the heat is transferred from the higher temperature hot air across the pipe wall through conduction, by conduction, then to the fluid. So you can see that you have resistance to convection, and then for conduction through cylindrical wall is re-expressed in this new equation that we learned today, right? The outer radius minus the inner radius divided by the thermal conductivity of the pipe wall, right? And then the log mean area of the pipe wall, right? So we use this if your A2 divided by A1 is greater than 1.5 or equals to 1.5. All right, so plus the resistance to convection, right? Heat transfer by convection in the fluid, right? From the surface of the inner pipe to the fluid. So now, if we want to express this, all right, this whole equation in terms of the overall heat transfer coefficient, it depends whether you want to express it based on the inner surface area or the outer surface area. You can try it, right? If it's in terms of inner surface area, you notice that, so you just imagine, all right, so here you multiply here, this section, we talk about this section with AI, right? Then this will cancel out, all right? And then here you have AO divided by AI, which you can see here, AO divided by AI, all right? And then here you notice that, all right, so because you multiply AI, right, so there will be AI here. Okay, same goes to case, okay, let's say I erase this. Let me clear this. All right, so let's say if you multiply this with AO, right, so this part here we multiply with AO, so then this will cancel out, but you have AO over AI for this first term here, then second term here you have AO divided by the log mean area, as you can see here. All right, so it depends whether you want to express the overall heat transfer coefficient in terms of inner surface area or outer surface area. Okay, all right, so yep, that's all actually for today's lecture, where we visit back on the basic part on heat transfer, the three modes of heat transfer: conduction, convection, and radiation. And then we look at the conduction equation for slag, hollow cylinder, and hollow sphere. Then we look at how to calculate the conduction in series and parallel, and also for combined convection and conduction. Right, that's all for our lecture today. Now, before we end, don't go first, okay? So just a quick check. Has everyone taken your attendance? Has everyone taken your attendance? Okay, let me check again how many have taken the attendance. Only 18. Yeah, I think then that's only 18 because I can see there's only 19 joining the session. Okay, just a moment. Well, I need to brief you on something. Okay, just to update your okay, you want me miss it. Let me generate it. Give me a minute to generate the this ribbon is irritating. Can you see the screen that I'm sharing? Are you able to see the screen that I'm sharing? Just to check. How can I do it on the same screen? Okay, I think I have to do it this way. Okay, yes, okay, good. Okay, but I need to check the chat area. Okay. Hold on, yeah. It don't allow me to minimize it. Okay. Let me rearrange it on my side. Okay. Now if you check my times, right, I've updated the lab timetable. Actually, not much changes. It's just for one group. Oh, Yomi, sorry. I mentioned that I need to give you the passcode. One, yeah. Okay, we still have like around 7 more minutes. Okay, now for your lab, it will start for some group. Let's look at the timetable. So for group 1 and group 2, your lab session will start on next week is week 5, right? Next Thursday, 2 to 6 p.m. It's at the Energy and Fluid Lab. The one you all did the experiment for thermodynamic and heat transfer, where you can see the boiler one, right? So for group 1, we have 5 students, but group 3, it's down to 3 students because Alvin dropped the module. So Yomi has agreed to join group 3. So group 1, take note that you have only four group members left. And then for group 4, right, I've checked the system. Boyan still registered with the module, but when I checked his attendance, he has been like absent for 3 weeks, not only for AHM but for other module as well. Anyone is from the same cohort as Boyan? Are you still in contact, and do you have any idea whether he's still like is he transferring, or is he going to continue his study at Taylor's? Because he has been absent for all the module, I think. Anyone has any update about this? Oh, do you mean he's traveling? Or he transferred already? So which means he will not be joining. But I think, yeah, he's not in Malaysia. Okay, thanks Bernard and Eamon for the update. But no worries. For group 4, Adi is still with you. I'll just chat with Adi. All right, so group 4, you still have 4 students anyway. All right, so it's sufficient. Your manpower is sufficient. So every group you have at least 4 students, right? That will be sufficient. All right, so for week 5, we'll start. You all have decided to do 2 experiments at the same time, right? Because each actually only take 2 hours. So you can submit your lab report according to this timetable, which means if you are supposed on week 5 to complete your first report, right, on post-convective heat exchanger, then that will be 2 weeks. Then even you complete another one in advance, just for this module, just for this module, right, you can submit your another report friction loss by week 9 then. Okay, please don't quote my name. All right, so only for this module, all right, so you can submit your lab report according to this timetable. Okay, so I think for this module for Thursday, there are no public holiday, so all your lab session will not be affected. So you just come according to the timetable. As for group 5, right, you all can discuss if you find that it's hectic for you to complete both experiment on week 7, right? If you want to split or you want to postpone it to week 9 to complete all together, just let me know in at least a week in advance. Okay, you all discuss about it. But also take note that by usually week 11 or 12, you may need to submit assignment for other module. So you plan yourself when you want to do the experiment. Okay. Now, before that, all right, so think also please, all right, so it's from today onwards, you can start to check your lab manual. What is it about? So for this post-convective heat exchanger, right, I've uploaded this reference here, right, which you can have a look, right? It's a sample question. It's related to what you are going to do with the post-convective heat exchanger and how we are going to analyze the rate of heat transfer and the temperature change. So, and then for any submission of the lab report, please submit according to the submission box. I have labeled it. And then for friction loss of long applied, all right, so it's quite related to what we have done in lecture 2. You should be prepared already, but take some time to go through the lab report as well, so that you have an idea what equipment that you'll be using. Okay, so for this one, let me see. For this one, take note that you need to wear long pants, cover shoes, right? For girls, tie up your hairs, and then you do not need to wear any lab coat. All right. So the lab report is given here. Okay, let me see. Oh, unfortunately, we have to. Okay, there's a question. Each group, maximum 5 students only. But I cannot rearrange any furthermore because actually this grouping here is all approved by the program director already. So we have to follow it. Right, we have to follow this one. Right, so we cannot rearrange it further anymore. This is exceptional for Yomi to join group 3 because of the lack of manpower. All right, so we'll follow this. Okay, then another thing that I want to discuss with you also, for tomorrow, right? This one, if you refer to the question, is quite straightforward. I just want to ask your opinion. It's more like conduction, convection, combined conduction, and convection calculation at quite basic level. It may took like 1 hour, 15 minutes to 1.5 hours. Do you all want to do it online, or do you all prefer physical to travel to the campus to just attend this tutorial course? I'm not quite worried on you all on sewing this one. I think you all have some knowledge and skill already. So just want to check with you all. Do you all want to do it online for tomorrow or physical? So if you all prefer online, perhaps then everyone can do a thumbs up. Let me see how many prefer physical. For those that prefer physical, can you? We have 2 that still request physical. We'll need to see majority. 3 for physical, so we have 19 students, right? Okay, I think if there are 3 student requests for physical, then we will need to do physical then. Okay, then I think a lot of requests for physical. So if you're willing to travel, then I'm okay. All right, just to check with you all. Because I worried then if you attend the class and you see all the questions so simple, then you'll be wondering why you still come for a class. All right, then. So tomorrow will still be a physical class, but please, I need your help, right? So come on time at 4, so that some students that don't have 6 p.m. class, then they can leave earlier. Else it will be very jammed. All right, so we'll start the class latest by 4:05, no matter how many students join. Okay, all right, so we'll meet in class tomorrow then. Okay, thanks. So yep, today we'll end our class earlier then. Do you all still have any question? Any further question? So if no, then that's all for today. We'll meet tomorrow. Okay, thank you. Tomorrow class at campus. Okay, thank you.